So we're talking about annihilation. We're saying if you get an antiparticle, particle, smash them together, and you produce two photons. Why two photons? Because you need to conserve momentum. You had two particles that, yes, they had opposite charges. One was anti-particle, one was particle, but they both have mass. There's no, even antiparticles have mass. They don't have anti-mass or anything like that. It's, it's all mass. And Einstein's famous equation shows that there's an equivalence between mass and energy. You can convert between the two. And this is one of those instances. C, speed of light, 3 times 10 to the 8. That's a huge number. And then you're going to square it. So for 1 kilo of mass, you're getting a gargantuan amount of energy. So mass is essentially very, very concentrated form of energy, which is a very tempting proposition for, nuclear reactions. There's no wonder why we were so keen to crack open the atom. So it implies that any change in the mass of a system is accompanied by a release of energy. Yes, that is true. Binding energy, we'll see in a bit, manifests itself as a change in mass. So consider an electron and positron, both of mass 9.11 times 10 to the minus 31, annihilating to 2 photons. The change in energy before and after is the change in rest mass, mc squared. So we had 2 times 9.11 times 10 to the minus 31. That's pretty tiny still. Times 3 times 10 to the 8 squared, which is, of course, 9 times 10 to the 16. Plug that into a calculator, and I got 1.6398 times 10 to the minus 13 joules. You might say, so what? That's tiny. But that is literally only 2 electrons, not even atoms. An electron and a positron. The head of a pin will contain trillions. So there's plenty of energy floating around. All of that energy is going to form 2 protons, and the energy of to say protons, I meant photons. The energy of a photon is Planck's constant multiplied by its frequency. Okay, so that was mass. That was the annihilation of mass to produce energy, but a slightly more subtle version of the interaction between energy and mass is when we talk about binding energy. I always struggled to understand this when I was a student, actually, binding energy. So let's pay close attention to definition in the red box. The binding energy of a nucleus is the total work that must be done to separate a nucleus into its constituent nucleons. Okay, so a nucleus is bound together, which in itself is a bit of a mystery because you would have thought all these positively charged protons were aching to get apart. But no, there is a force stronger than electromagnetism, and it is the strong nuclear force, and that's keeping the nucleus together. That force has to be overcome, so you need to put in some work, tear it apart, and then suddenly, if you remove all your constituent nucleons far enough away from each other, they won't have an effect on each other, so remove them to infinity. That total amount of work done, that's the binding energy. The mass defect then, actually, before we move on to the mass defect, so I've just done a bunch of work to separate. If I've done a bunch of work to separate them, that implies I've put energy into the system. That's correct. Where has it gone? It's increased the potential energy of all these particles. And when we're talking about electrostatic potential, these are, protons, they repel each other. Therefore, Therefore, if I'm doing, actually, no, sorry, forget the fact they're protons. They are all nucleons and they are bound by the strong nuclear force. That's the key operating. And so when they're in the nucleus, they sit in a potential well. And it's a well that you need to get them out of. And so in removing them all to infinity, I have to put in a certain amount of work. And that is the binding energy. Okay. It feels odd to me, and it maybe feels odd to you, that the binding energy is defined in this way in this sentence that is talking about tearing things apart. You know, you think it would be better called the tear apart energy or something. But yep, all the work I'm putting in to separate them results in an increase in potential energy. Why potential energy? Well, because at any point, if the band got back together, if they reunited, work would be done by the fields to bring them back together. So that work can potentially be used, hopefully. If I'm giving them all energy, it means that the mass is going to increase. And the mass defect is the difference in mass between a nucleus and the sum of its constituent nucleons. So the sum of masses here is greater than the united mass of the nucleus. Okay, so it's this mysterious process where you have a nucleus, you crack it open, and if you put all the constituents on a measuring scale and weigh them individually and add that all up, you end up with a bigger number than when you started. Why? Because I've put in energy, and energy and mass can be interchanged. Okay, the mass defect is associated with a release of energy. Yep, I agree. So let's put this to the test. What is the change in mass? My final mass is 6 times, oh golly. I told you that the mass of protons and neutrons was similar. It's 1.007, 1.008. So, you know, there you have it. Okay, there's your final mass. Your initial mass is just this 13.00336. That is equal to, the change in mass is equal to 0.10101 U. Okay, so the change in energy is the change in mass times c squared, which is 0.10101 times U, which is 1.66 times 10 to the minus 27 times c squared, which is 9 times 10 to the 16. Put that all together and you end up with 1.51 times 10 to the minus 11 joules. Okay, so that's one nucleus. If you split it apart, you get something on the order of 10 to the 11 minus 11 joules. You might again think, oh, that's tiny. In electron volts, considering an electron volt is 1.6 times 10 to the minus 19 joules. So you're talking something on the order of 100 million times larger than an electron volt. At such a small scale. It's pretty powerful. So don't underestimate it. Okay, exemplar exam question. Calculate the difference between the energy required to break a sulfur-32 nucleus into 8 alpha particles and into its individual nucleons. Okay, it's a very similar question to what we've just done, but this time, haha, I don't have to write anything because it's all pre-written for me. Okay, so the change in mass, you finish the first. If you're splitting it just into your alpha particles, your final mass is 8 alpha particles. And you subtract the original mass, you get a mass defect of 0.04 U. And the energy gained, multiply it by c squared. You get not quite as much energy as last time, roughly about half as much. 5.97 96 times 10 to the minus 12 joules. Okay. How about if we split it even further into the individual protons and neutrons? Yep. So bear in mind they didn't actually tell us how many protons and neutrons were in sulfur 32, but it told us it broke down into 8 alphas. We know each alpha has 2 protons, 2 neutrons. Okay, so we can do a bit of deduction. Break it down, and instead of 0.04 U, you get 0.284 U. 0.04 U. Okay. So you've gone from effectively 4 to 28. So that's going to be a 7-fold increase, which is awesome. Or 7-fold multiplication, technically. Sorry. Calculate the energy released, and we're back up to the level of 10 to the minus 11. Great. What's the difference in energies between these two reactions? Oh, look, it's a numbers game. If you